welcome to the second session of SIGCOMM today. This session consists of 5 papers on 5G networks. The first presentation is about the mobility management in 5G cellular network. The presenter is Ahmed Hassan from University of Minnesota, Twin City. Ahmed is a second-year PhD student in the CSE department. His advisor is Professor Feng Chen, and they work on topics such as mobile systems, 5G, mobile networks, and the network VR/MR. His current research highlights challenges faced by today's 4G and 5G applications and argues for a cross-layer design for overcome these challenges. Unfortunately, he couldn't be here physically to present his paper. Please play the video first.
Hi everyone, my name is Ahmed Hassan, and today I will be presenting our work, Vivisecting mobility management in 5G cellular networks. The 5G networks have been growing very fast since their inception, and improved mobility was one of the promising features of 5G. We noticed that mobility management practices of today's 5G are still unknown. In our work, we identify these practices, highlight their issues, and describe what can be done to fix these issues so that mobility can be improved in the future. So, we know that cellular carriers use an umbrella of radio cell towers to dispense their services. And to support user mobility, the carriers use several mobility management procedures, such as handovers. So as a user moves from one place to another, their mobile device undergoes a handover that transfers the state of a mobile device from source cell tower to a target cell tower. But the network activity gets interrupted while the handover is being executed. So the question is, why is it important to study 5G mobility management? And one reason is that 5G has made mobility management much more complex than previous generations of cellular technology. For example, small coverage of 5G base stations result in frequent handovers. Additionally, the current radio network deployments are very diverse. For example, the carriers are using 4G and 5G at the same time. And within 5G, we have standalone SA and non-standalone NSA architecture of 5G, which leads to long handover durations. Finally, the diversity of radio frequency bands in 5G leads to frequent network fluctuations, which has a cascading impact on application performance. Now the question is, what's the impact of mobility on application performance, and how do we measure it? But does handovers cause excessive energy overhead on mobile devices? And what implication does 5G mobility has on cellular networks? And what can be done to reduce performance degradation caused by this mobility? So to answer all these questions, we mainly investigate 4 key directions. First of all, we study how 5G handovers impact the application performance. Second, we examine the key characteristics of 5G handovers. For example, what is the duration and frequency of each handover type, and how much energy can a handover incur? Then, we shed light on the implications of 5G handovers on cellular networks. Here, we also identify new issues and challenges that are faced by 5G networks. To do that, we conduct a cross-country driving trip with data plans from 3 major 5G providers. Finally, we use insights obtained from our analysis to explore 5G handover prediction problem. We develop a framework called Prognos that can mitigate the negative impact of frequent 5G handovers. So to conduct our measurements, we set up a comprehensive measurement testbed comprising of multiple smartphones with access to 3 major 5G providers. We also have an updated version of custom-built Android tool, 5G Tracker, that captures mobility-related information on unrouted smartphones. We also have a professional tool, XCal, that collects cellular control plane messages on mobile devices. And we have a physical power monitor to accurately profile mobile phones' energy drain. So using this testbed, we cover a distance of more than 6,200 kilometers across the US and carry out several types of measurements. So first, we focus on the impact of mobility on application performance. Previous studies have looked at the impact of 5G handovers on network throughput. But the impact of mobility on application QE is still unknown. So we use a mix of latency-sensitive and bandwidth-hungry applications to point out the factors that impact QE fluctuation during mobility. And the applications that we consider in our study are live video conferencing, 4K cloud gaming, and volumetric video streaming. So first, we identify the factors that contribute to the mobility-induced QE fluctuations. We did a series of experiments and found out that radio access technology, handover type, network architecture, radio frequency bands, and 5G deployment mode are the factors that determine the severity of performance loss due to mobility. So as an example, we ask the question that do all handover types have similar impact on application performance? And the answer is no. To explain this, we use a trace from cloud gaming experiments and differentiate handovers based on radio type. We have two subplots here. In the top plot, we have network latency on the left y-axis and other latency on the right y-axis. Network latency is the time to transmit a rendered frame from the cloud to the mobile device. And other latency includes delay for rendering, encoding, decoding, etc., which typically remains constant throughout our experiments. The bottom plot shows us the percentage of dropped frames. We find that in NSA 5G, handovers on 4G radio incur 2.26 times higher latency and 65% higher drop rate as compared to 5G radio, which means that handovers on the 4G radio are main culprits of performance loss in NSA 5G. Then we dive deep into the characteristics of handovers using the dataset that we have collected through our drive tests. So through our analysis, we confirm that 5G handovers are indeed more frequent and have long durations. So the question is, can 5G handovers incur high energy overhead on mobile devices due to their frequency and long durations? So to answer that, we log the energy profile of mobile devices during handovers. So here on the left y-axis, we have power consumed by a single handover. And on the right y-axis, we have power consumed per unit distance, which also takes into account the frequency of each handover. So we have a few interesting insights here. For example, we found out that low-band handovers consume more power per handover when compared to millimeter wave. But if you look at power consumed per unit distance, millimeter wave handovers are still more costly overall because they are more frequent than low-band handovers. To make the results much easier to understand, consider a smartphone traveling at 130 kilometers per hour for 1 hour. So during this time, NSA low-band handovers will drain 34.5 milliampere battery, while millimeter wave handovers will drain a drastic 81.7 milliamperes battery. And using this much energy, an S20 Ultra smartphone can download 4.3 GB data on NSA low band and 75.4 GB data on NSA millimeter wave. We encourage the audience to read the detailed energy results in our paper, which suggests that handover energy consumption in 5G is non-trivial due to high signaling overheads. Now, let's take a step back and see what we have discussed so far. So we have established that mobility management in 5G is much more complex than previous generations of cellular technology. We also found out that 5G handovers severely impact application QoE, and the level of severity depends on multiple factors. We also discussed that handover durations are long in 5G, and handover energy consumption in 5G is non-trivial. Next, we focus on the implications of mobility on 5G networks. So to understand the impact of handovers on network bandwidth, we perform bulk download using iPerf to saturate the downlink channels of the mobile phone. We plot the downlink throughput before, during, and after the handover. Here we focus on simple 5G to 5G handovers. So you might know, handovers within the same technology are expected to improve the network performance after handover execution. But that does not happen in NSA 5G, as the average post-handover throughput reduces by 14% compared to pre-handover throughput. We also observe no signal strength improvement after the handover in the case of 5G to 5G handover for all the operators. This is because in NSA 5G, a 5G to 5G handover consists of a 5G to 4G and then 4G to 5G handover, and both handovers are done independently without accounting for the overall 5G to 5G signal strength improvement. So we suggest that cellular carriers can improve their 5G to 5G handover logic by considering the overall handover sequence. We also investigate how the co-location of 4G and 5G antennas impact the handover duration in NSA 5G. Remember that in NSA 5G, the UE connects to both 4G and 5G antennas, which may and may not be co-located with each other. So if the antennas are co-located, we can reduce the communication latency between 4G and 5G antennas. So during our analysis, we find that handovers where 4G and 5G antennas are co-located incur 13 millisecond lower latency compared to the other case. This suggests that cellular carriers can lower performance degradation of NSA 5G handovers by considering the 4G and 5G antenna locations when they are doing the handovers. Next, we investigate the handover prediction problem in the context of 5G. And the first question is, what can we do to mitigate the impact of handovers? So we argue that if we can predict handovers and then estimate the network fluctuation that is caused by these handovers, then the applications can act proactively to reduce the performance degradation that is caused by these handovers. So let's first try to understand how we predict the handovers. So as you might know, the handover procedure starts when the mobile device starts monitoring its radio environment, mainly to see if some neighboring cell tower is doing better than the serving cell tower. If that is the case, a measurement event is triggered and its report is sent to the cell tower. These events are pre-configured by the radio network. So when a report is sent, the cellular tower makes a handover decision. The black box handover decision logic changes based on geographic area, handover type, access technology, and many other factors. So if the radio network decides to do a handover, the handover command is sent to the mobile device, which moves the mobile device from one tower to another. So we model our handover prediction system according to this handover state machine. So our system Prognos has three main components. First, the report predictor monitors the radio environment and tries to predict measurement reports. Then the decision learner learns the black box decision logic in an online fashion. And finally, the handover predictor combines results from report predictor and decision learner to predict the handover. To estimate the network fluctuation that is caused by these handovers, we look at handover type that is predicted by our system, and then empirically calculate a score that quantifies the change in network capacity due to that particular handover type. To validate the usability of our system, we apply it to two applications, 16K panoramic video streaming and volumetric video streaming. Here, we show 16K video streaming as an example. We simply correct the throughput estimation of ABR algorithms based on the predicted handover fluctuation. To see why this works, we compare the performance of original ABR algorithm and our modified ABR algorithm. On the y-axis, we have mean average error in throughput, which simply shows the difference between the throughput estimation of ABR and ground truth throughput. Here, we take fast MPC as an example. Fast MPC PR is our modified version. As you can see, the throughput estimation of ABR algorithm degrades when there are handovers. And Prognos helps improve the throughput estimation of fast MPC. This improvement also translates into QE gains. Here, we show the QE of three ABR algorithms. X-axis is stall time, Y-axis is normalized bitrate, and QE increases in the top right direction. Apart from the original ABR and ABR with Prognos, we also show the QE of ABR algorithms with ground truth handover information. Our results show that Prognos reduces stall time by 34.6% to 58.6%, and it is within 1% of the ground truth. Coming to the key findings and takeaways, we find that 5G handovers severely impact application QE, and the level of severity depends on multiple factors. We also show that handover durations are long in 5G due to the interactions between 4G and 5G radios, and handover energy consumption in 5G is non-trivial. We also highlight handover performance issues in 5G, and we also suggest improvements. And finally, we design an on-device handover prediction system that outperforms existing prediction methods, and we also demonstrate its usability. So to conclude, we perform a comprehensive investigation of mobility management in 5G, and we do that from multiple perspectives. And finally, we also explore handover prediction problem. Thank you.
Any questions? Hello? My microphone does not work. Any questions? We can take a couple questions from the audience.
No. No, it's not. Go ahead.
Okay.
Not working. Oh, no, it is. No, it is. Okay. Thank you for your presentation. One quick question. So, do you think this handover is mainly because of the deployment of 5G currently, and it will change over time, and you will see less handovers, or is that an inherent problem of 5G?
Okay, so I think you guys can hear me. So the question is that is it inherent, like the performance issues, are they inherent, or will they improve with, let's say, 6G or next generations of cellular technology? So it's not the problem of 5G, it's the problem of non-standalone architecture that is being used in 5G. And it is here to stay, because in future we'll still have existing 4G architecture, and we can have like different type of NSA deployments. They will upgrade, but still the NSA architecture will be there, and these performance issues will still exist. Now the frequency of, like, talking about the frequency of handovers, so they depend on multiple factors. So if you are using let's say millimeter wave or midband, then the frequency of handovers will be high. If you're using low band, it will be low. But we are mainly like focusing on the architecture type, NSA or SA. So that's what we have been like talking about in this paper mainly.
Thank you.
That basically causes the handovers to be more frequent. Yep.
So I'm trying to puzzle out an odd question that came up as you were talking, which is, how do I translate that energy consumption on the handoff into how much work I'm willing to do in the handset to reduce the cost? As you just express it as an energy budget, but you might as equally well express it as an instruction budget. How much of the CPU, or how much time, or how intensively, how many cores would I be willing to run on my handset briefly, and actually save energy by doing something smarter in the handoff process, doing even better prediction or such like? Do you have any sense?
Yes. So yeah, that's a very interesting question. So I think let me quickly repeat that question. So I think you are trying to ask, like, what is going to be the trade-off if I do something smart and try to reduce that energy overhead, right? So we can do a lot of things. First of all, we basically came up with Prognos system. We haven't looked at its energy overhead because we couldn't like deploy it in real real world smartphones. So that was like one of the issue. That's why we basically tried to make it basically more make it more understandable for the audience and for the reader. So that's why we converted into downlink speed and that kind of thing. Converting it into, let's say, CPU usage and all that, I think it's not that straightforward for what I can think right now. But definitely we can explore that. Maybe I can discuss this like offline with you. Would you mind sharing your name and contact?
Sure. Craig Partridge. I'm at Colorado State University. Google works.
Are there any other questions?
Yeah, KK.
I have a quick follow-on question to the first one, where you were saying that because of NSA, this 5G to 5G handover goes through a 4G intermediate handover. Is that a temporary thing, or I would expect that this handover process is something that when you have a handover from 5G to 5G, you don't really need to go through that intermediate process at all.
This basically happens because 4G basically controls all the control plane signaling. So 4G is kind of the anchor here, okay? And you have to do everything through 4G. So let's say, and there are many scenarios, let's say, so if a handover is going to happen on the 4G radio, right? So that will basically affect your 5G radio as well, because you will lose your control plane signaling, or like control plane, like you will lose all the operations, right? But if a handover is going to happen on 5G, then it might be less drastic, and that's what we basically mentioned in our paper. So basically, you also asked if, let's say, that intermediate procedure can be removed from here or not, or if, let's say, we can optimize it. So for NSA, it's not possible right now to optimize it. 3GPP has basically introduced some new type of handovers in release 16 that, like, some cellular carriers and smartphone manufacturers might implement in future, but I don't know, like right now they don't have like anything like that we can test.
Okay.
But yeah, there are some algorithms in the design.
Okay, all right. Thank you for the speaker. So the next